All right, welcome everyone. Thank you for attending our talk. I'm Guillaume Masse and this is Martin Duhem. We both work for the Scala Center. The Scala Center is it's a nonprofit organization for open source and education. And during the open source part of our work, we both worked on Scala Native. If you want to know more about the Scala Center, you can watch the previous Scala Days 2016 keynotes by Eder Miller. And this is the plan of this presentation. First, we'll present what is Scala Native, and then we'll walk through a demo. It's a bandwidth monitor, and we'll implement this during this talk. I will set up your system and set up the project, and then implement the application in 4 segments.
All right, so first let's see what is Scala Native with a bit more details. Scala Native is an open source project that aims at compiling your Scala source files to native code. It has been started by Denis Chabalin, who is a PhD student at TPFL. It was started around August 2015, but it has been publicly announced last year at Scala Day. The compiler is open source. You can find it on GitHub, and you can tinker with it, read the source and everything. So, in a few words, how does it work? So, you probably know that on the JVM, you use Scala C to generate class files from your Scala source code, and then those class files are going to be interpreted by the JVM. On native, we still use Scala C to compile your Scala source files, but we also emit our own representation of the program. We work on it a little bit, we optimize the code and so on, and then we convert it to LLVM's representation in LL files. Then we give that to LLVM, which will generate native binaries. LLVM is a compiler project that has its own representation of programs that is very generic. You can compile many languages to it, so that then you give the rest of the work to LLVM and generate native binaries for many architectures. So you can compile to ARM, x86, or 64 bits, and so on. Now the features of Scala Native. The first release has been made about 2 months ago, and in the first release we already had a really nice C interoperability. So we'll see many examples of this in this talk, how you can use stuff defined in C from your Scala code. We also had a really nice story, the garbage collection, so that you don't have to worry about allocating and freeing memory, just like you do in your usual Scala code. The applications that are compiled with Scala Native, they also start very fast. Unlike on the JVM, where you have to pay the cost of initializing the JVM, warming it up, and so on, it's immediately very fast. Also, we have a nice IDE support. So if your code works nice with Scala JVM in your IDE, you won't have any issue with the day you start working on Scala Native. And finally, we have nice SBT integration. You just have to drop the SBT plugin inside your build definition, and you can get started with Scala Native. In the second release of Scala Native, we more focused on making the standard library bigger, so that you can use more stuff that exists on the JVM, like regexes and I/O. We had initial support for futures. We also added things that were missing on strings, characters. We added support for system properties. So in this release, Scala Native really started to feel more like working on the JVM. The upcoming release of Scala Native, it should be out very soon. We have a much improved garbage collector. If you were at Denis's talk yesterday, you may have seen that there will be a nice performance improvement if you enable the new GC. Also added support for NIO, jars, zips, and we also hope to have a nice SBT test interface. So the goal here is to be able to compile your tests using usual test frameworks in Scala and run them on the JVM or on native so that you can make sure that your program behaves correctly at the same time on the JVM and on native. In the future, we will work more on improving the interoperability story. So that's the work that Denis is going to be doing. We also have an open pull request for Windows support that has been contributed by an extra contributor. And also we'd like to have automatic binding generation. So that's something that should be able to generate the glue code between Scala and and C, and it will make it easier to use stuff defined in C. So here we have an example of a program that runs first on the JVM and then on native. As you can see on the JVM, you have to wait a little bit before you get the output. So that's the version on the top of the screen, and below it's really much faster. This is Scala FMT, by the way. And this was enabled by the recent work that we done on regex, I/O, and many other things in Scala Native.
All right, thank you, Martin. For the remaining of the presentation, we'll implement an application. It's a bandwidth monitor. This is an existing C application, so we ported it to Scala Native, and this is how it looks like. So it's an application that runs in the terminal, and you may have similar application with graphical interface. So the top part, it shows the received packet in your network interface, and it's the bandwidth over time. And this is how it looks like when I run on my computer. All right. To get started with Scala Native, you need to set up some system dependencies. So this is how you do it on Mac, Ubuntu, and on Linux is a bit simple. What is highlighted is what you need for the Scala Native normally. And then for this application, we'll need the ncurse library, which render things on the screen. To set up Scala Native, it's really simple. You only need a SBD plugin. So on the first line, I add the SBD plugin, then I enable it on my build. And that's it. So here's the plan for the implementation. So first, we'll create a function that will call another function each time, so each second, so we can continuously draw on the screen, for example. And then we'll find the network interface. So if you do ifconfig, for example, on Linux, it's the string like ETH0, so this is what we're looking for here. And then from this network interface, we'll get the bitrate, so 34 kilobytes per second, for example. This is what we want to pull. And finally, we'll accumulate this information over time, and we'll draw a graph on the screen. All right, so this is the first function we want to achieve. So it's a function that continuously prints something on the screen or executes its body. And we have our main method. Pretty straightforward. On the left part of the screen, this is how you implement it in C. And on the right-hand side, you have it in Scala. So let's study the C part first. Not shown here in this code, we have a draw function. It's a global function that we want to call each second. To do so, we have to call getTimeOfTheDay inside of a loop, pass it a structure called timeVal, and we want to see if the second bit increments. So if it does, well, we jump in this branch, and we draw what we have to draw on the screen. For the Scala code, it looks really similar. The only difference is that we don't pass a global function. We can pass our function in the parameter. So this is the function body. To allocate things, we can use this method called stackAlloc with the type, so timeVal, and it will return a pointer to this structure. It's a bit different than C, because in C, it will return the value. And since we have a pointer, we don't need to dereference, so we can call this function. All right? In order to call this function, we first need to define its interface in Scala. On the left, you can see this function, getTimeOfTheDay, written in C. And on the right, you can see the Scala again. So getTimeOfTheDay, to call getTimeOfTheDay, you need to pass it a timeVal. It's this structure here. So in Scala, we define it with cstruct n, where n is the number of types we want to pass it to the field. In this case, we need to, the structure has two fields, so time t, and it has also the second field, which is the amount of microseconds. Since we're in Scala, we cannot have top-level functions like in C. So we use the @extern annotation to specify that in this object, we need to search for external methods. And to define an external method, we use the extern method. So this means that when we call this function, we need to call native code. All right. So on the previous slide, we saw that with cstruct, we can define the type of the fields, but we cannot define the name of the fields. Like here, you have the type and the name. So to define the name, we can use this implicit class here. So we will augment a pointer of time val to be able to fetch its different fields. And here, this symbols means that you want to access the value of a pointer. And here we use a tupled-like syntax where _1 fetches the first field of a struct, and _2 fetches the second field of a struct. So this is the delta between C and, well, this is how you do it in Scala Native, what you normally do in C.
All right, now that we can periodically print stuff on the screen, let's see how we can interact with the network interfaces and retrieve them. So on the left of the screen, you have what you would typically use to retrieve the interfaces. The struct here is the definition of an interface in Linux. So inspecting its fields, we see that it has a pointer to another of the structs. So we have here a kind of linked list structure. We have also the name of the interface, some flags, and some data that we'll talk about later. And to retrieve the interfaces, we have this function that will also allocate some memory to hold the interfaces, and the free function that will free the memory allocated for the interfaces. Again, in Scala, we define an external object, so nothing new here. We have the two functions. We simply translate the signatures. And we define the struct that has 7 fields now to hold one interface. Because in Scala, we can't do something like type x equals list of x, we can't use, again, this type that we're just defining here. So we have an issue with the linked list structure. What we do instead is that we use a pointer of cbyte that will cast whenever we try to use this particular field. Apart from that, nothing new. We continue to define all the fields and translate the signatures. As I said before, we use some flags inside the structure to present some information about the interface. So it's really nice here that we can use very low-level values, but still benefit from the complex and powerful type system of Scala. So we define a class that will just wrap the type of that will just wrap the flags and define some operation on them so that we don't shoot ourselves in the foot while doing, well, let's say, adding 2 flags. We can also give meaningful names to the different flags so that it's easier to read, but we still have the underlying C value. Again, we define some enrichments to give names to all the fields of the struct. As I said here, because we could not use directly the actual type for this pointer, we cast it when we try to use it. Also, we can define an iterator on the linked list of interfaces. So that's nice, again, to define a higher level construct that is working with really low level stuff. So now that we know how to represent an interface, let's see how we will interact with them. So here we're defining a higher order function that will take an operation to do on the iterator of interfaces and produce some result. We allocate some memory to hold the pointer for the interfaces, and we retrieve all of them from the operating system. If everything goes all right, we get a return value different from -1, that's in the doc for this function, and we will apply our function on the interfaces that we just retrieved. Then we free the memory for the interfaces and return the value that we just computed. So it's nice to be able to define higher level construct, higher level functions that are working on very low level structure, because after all, we're still getting the interfaces from the kernel, so it's very low level, and still we manipulate them using higher order functions. Now that we can get all the interfaces, we still need to find the one that we're interested in. So to do this, we just find in the iterator an interface that is at the same time up, running, and which is not loopback. Because monitoring loopback or an interface that is not running is not very interesting. Finally, we can extract its name. Because in C, we have different representation for string than we have in Scala. We just use the function from CString that will convert the C representation to our representation of a string. And finally, we get the name of the string, of the interface that we wanted to find. All right, now that we have the interface, let's extract the bitrate from the interface. To do this, we define a case class counters that will just hold the number of bytes that have been sent and received from the interface, and a companion object that will help us to instantiate the counters from the statistics of the interface. That's very simple. We just get the Rx bytes and Tx bytes from the statistics. To get a counter from the interface name, we find the interface as before. And if the interface has just seen a packet, we know from the documentation of the Linux kernel that at this moment, the data pointer of the interface has a pointer to a struct that represents statistics about the interface. So we can just get those statistics, fill them in the counters, and continue. All right, this is how you would do it in C. So as you can see, the code is a bit longer than all the code that we had in Scala in just one method. But that's because this function is doing a lot of things. At this line, it's getting all the interfaces and returning if something is going wrong already. Here we are walking through all the interfaces. Here we're trying to find the one that we want. Here we're testing if this is a packet, extracting all the information, and finally returning after freeing the memory for the interfaces. So this is not really how we are used to do things in Scala, because we are getting those two pointers as parameters, Tx bytes and Rx bytes. They act as kind of out parameters. We'll just modify their values. And we also return an int from this function, which which represents if the function returned correctly or not. So this is not really idiomatic Scala. And also we have we have lots of concerns inside the same function. At the same time, we are making sure that we free and allocate memory, trying to find interfaces, walk them, and so on. So it's much better to have a modular implementation for this. Something else that we must be careful about when working with native is that some structures may have more than 22 fields. In C, you can go even beyond 1,000 fields, but our current implementation in Scala Native supports only up to 22 fields. So, because if we have really that many fields, we must generate in Scala Native all the different definitions for those structs, and supporting up to 1,000 fields would mean that we would have to generate really many, many lines of codes, and that would be a bit too long. So in our case, we are safe because we are just interested in the third and fourth fields of this struct. So we have no issue. And also, we are not trying to allocate memory for this struct. So if we try to allocate memory for this struct, our definition in Scala Native would only allocate memory for the 22 first fields. So that would be not enough to hold the whole struct, and giving it to C would be a bit dangerous afterwards.
Yes, thank you, Martin. So we're not alone. We have 22 in Scala, but in C they have 1,023, so we're still limited. All right, for the remainder, this is how we can collect the information, collect the counters that we receive from the packet, and then draw them finally on the screen. So this is the top level part of the program. So we use this wait loop that I defined on the first segment. So this will be called each second. So each second, we use Martin's part where you get the counter, and we'll add them to a structure called history. I'll show this on the next slide. And then we can draw them on the screen. So draw the two graphs on the top, if you remember, and then we have the statistics on the bottom. And we call this doUpdate function that is required by Ncurse. All right, so to draw things on the screen, we use a library called Ncurse. So it's like you can draw on the terminal. So you have three useful functions really in Ncurse. You can create a new window. So window is just like a little box that you see on those old terminals, like if you go at the grocery store and they have those super blazing fast application that has like a border. Well, this is most probably using Ncurse. And you can also print a formatted string on the screen. So you specify the window and the position where you want to print that output, and you put a formatted string with its arguments. So just like the printf function, and it will draw those characters. And lastly, you can also print only one single characters. So this is useful for us when we want to print a graph. We can draw little stars for the columns in the graph. All done. So there's some Scala Native specific instructions here. For example, the @link annotation specify that we want to link again Ncurse. So we don't have to specify -l for this file. Also, we can use the @name annotation to specify a different name in Scala than in C. So in the Ncurse, they have this name called newWin. I would prefer to call it new window. Why not? Well, we're special. All right. So at this point, it's really plain Scala code. And this is so important. Like, at this point, we have collected all the things, all the necessary information from the low-level code, so the Linux API. We can render on the screen. So at this point, this is where it really gets interesting. We define a function, a data structure called counters history. This data structure has two queues, and those queues are bounded to a certain length. Because when we render on the screen, well, the screen has a fixed length, and we want to accumulate value, and then the past is just history. We don't care about the past. We just care about a certain window size. And this is what we do here. For example, if we add a new counter, so a counter as the total running number of bytes, well, we can add it here to our queue. And if it overflows, we can just dequeue the last element, right? And we keep the total because we want to do statistics. What we get is the running total. But what we draw on the screen is the delta, right? It's the difference between 1 second. So we can render kilobyte per second, for example. And this is just a utility function where we can generate other functions like maximum and average. If you take a look at the C code, this is really repetitive. It walks through the array in really different ways. It walks through the array of counters to compute the maximum. It walks through the arrays to compute the average. And this is really redundant, and in Scala we have a nicer way to do this with higher order functions. This slide is pretty loaded, but it simply prints the graphs on the screen. So here, for example, on the first graph, which is at the top of the screen, we can print the interface name. So if we pass a sum of something, well, we want to show the title of the application, basically. And then on this part, where, well, we use the maximum to scale the graph, and then we use our history to show the bandwidth over time, all right? So we have on the horizontal, we have the time axis, and on the Y, we have the bandwidth axis. So how many kilobytes per second. And what we do here is we select a way, so receive or transmit it. We start from the reverse of the queue because we print from right to left. and then we iterate over those columns, we iterate over those rows, and we print the characters until like it reach the top of one bin of the histogram. Does that make sense? All right. So let's show a demo of this running. So it's not that Scala Native is slow. We waited 1 second to get this first piece of information. So this is what I was saying. We print from right to left. Here we can see the different bins of the histogram, which are basically just single characters we print. We print the title here and etc. And the statistics on the bottom. Okay, 4 kilobytes per second. This is not a lot of network activity. So if we have some sound, we can play some video.
Developers, 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 developers.
So let's see the effect on the traffic. Oh shoot, Steve Ballmer just raised up the bandwidth. So it's up to 1 megabyte per second. All right.
All right, so now what is next, now that we have seen what we can do with Scala Native? You can just get this repository from GitHub, try to play with it, train for yourself, try to port it to macOS or something.
Yeah, it doesn't work on Mac, so sorry. I developed this on Windows, on Linux, so yeah.
Anyway, you can also try this SBT new Gittery template. So you just have to type this in your terminal, and you will get everything that you need to get started with working on Scala Native, hopefully.
Cool, the internet is working, that's good. All right.
So you have all the scaffolding that you need with a very simple build. We have a dependency on scopt that has just been released to Scala Native, and you can use it to parse your command line arguments. So this project is doing something really simple. At the moment, it just implements ls, and it supports just one argument. So maybe it can be a nice project to try to extend it so that you can see what you can do with Scala Native and see that it's really not that scary at all. All right, so once it's finished, we should get the list of files. All right, and also the binary that has been generated is in here, so that you can run it again and see that it's starting really fast. You can try to pass it option that does not exist and get a nice error message from scopt. And you can try to list all the files. Here we have a file .foo that has been shown that was not shown before. So it's a nice project to get started with Scala Native. And it has all you need to try to play with it. Do you get back to your presentation?
Yeah.
Oh, yeah. The source is really short because it's not doing that much. We're just getting the list of files using plain Java I/O, as you always do, and displaying it on the screen. Okay.
Yep.
All right, so as I said, you can try to complete it to get started with Scala Native. You can use it as a base to try to port all the utilities that I'm sure many of us are writing every day. And now you can write them in Scala and be blazing fast as well with them. Also, another idea that can be interesting is to use cross-project to cross-build your existing libraries to Scala Native and extend the ecosystem that is forming itself around Scala Native. You can try to port other command line tools to Scala Native. It's a very nice project. Or you can try to build things for Raspberry Pis. using Scala now. Thank you very much.
First of all, I'd like to thank you for giving a new definition to the term Balmer peak. But my actual question is around memory management. I saw you called a function called toC string. I didn't see anything about deallocating that string. How is the life cycle managed when you convert to a C data structure?
Because that was in the current version of Scala Native, the toC string allocates memory using the garbage collector. In the next version of Scala Native, it's going to be a little bit different. We have an implicit object that you can use to allocate memory inside what we call zones. So you can use the zone to allocate memory inside a zone, and when you get out of the zone, all memory that has been allocated will be automatically freed.
So is my understanding correct that since you pass it to some function, the garbage collector will see it as free as soon as that function returns, so this is safe at the moment?
At the moment, it's done with the GC, so at some point it will be deallocated.
But it can't be deallocated before it's used. That was what I was getting at.
No, if you keep a reference, it won't be deallocated.
Hello. So you showed how you can interrupt with C code. Have you thought about how, for instance, if you have a normal Scala program running on the JVM, how can that interact with a Scala Native program?
Okay. So you want to call Scala Native code from the JVM, is that correct?
Yeah.
So I'm not sure we can call Scala Native code from C. So like I would be thinking like you could use GNI to call like the C ABI, but maybe Dennis can correct me if there's a microphone for this guy.
Thanks for the feature request. I think only like 50 people requested this, so it might happen sometime in the near future, but not yet.
Cool. All right. We have another question here.
I'll try to make it more general than specific. What's the level of effort in, like, let's say you wanted to use MIDI functionality from Java Sound Library? You would have to take that and then just wrap the native C stuff that they've already wrapped? Would be a big level of effort?
So you have MIDI in the Java standard library?
It's a JavaX sound library, so it is standard, but I'm not. But I think on the different platforms, it's wrapping stuff.
Okay, so is it part of the JDK?
Yes.
Okay, so what we need to do, so basically, like most of our work, well, mostly Martin's work, so when we implement the JDK function, we have to implement it in Scala Native or in C. So this is mostly what we've been doing. For example, I implemented the regex, Martin did IO work and NIO, and so you have to be on the package like java.util.midi, for example, and then you implement this API using libmidi if it exists, and then yeah, it will be part of the distribution.
Was it a couple of days, a couple of weeks for a typical library?
It depends. For Java IO, it took me about 1 month, about one more for NIO. So it really depends on the size of the library. So
yeah,
and
the
depends
question.
also,
Would it be preferable to just wrap a C library using native C and then just call some C library that was already performant for MIDI?
Yeah.
Maybe another easier alternative, or just a subset?
So the first question was like, how much time does it take to re-implement those Java functions? It depends on the size of and the complexity.
yeah, if it's if the Java interface is really close to the one of C, it's really quick to do. You just have to define an external function like we did, just one line, and you put the signature, it's really easy. If you have more advanced function in the Java library, you have to wrap what you have in a C library and then re-implement all the complicated logic in Scala.
Mm-hmm. Yeah, it's just basically a constraint, right? Because if we go on the beginning, so Scala, the input of the Scala Native, it's Scala itself, not like the bytecode. So we cannot use like any pure Java library. We have to port it to Scala. So that's a constraint for Scala Native. Yes. So that's why we have to use the whichever native library that drives MIDI, for example. Yeah. Any more questions? All right. Well, thank you very much, and yeah, have a good conference.
Thank you.